Hello everyone, my name is Shine Russell and I'm going to talk about gradient descent. Gradient descent is best described as minimal cost, such as minima, by finding the values or parameters that affect the function the most. This means that you need to find parameters with the least or largest impact on the overall direction of the function as you try to get the lowest possible cost. To solve gradient descent, you will need to start to think about machine learning and also think about derivatives and other forms. In other words, to solve this, you will need a function such as the function right here, y equals x plus 7 squared plus 2x. So to solve this, you will need an initial condition. No matter what problem you're solving, you will always need an initial condition, and then you will also need a learning rate. This is more correlated towards the machine learning aspect of gradient descent, but it still helps to apply that concept even here. So to solve it, you go through multiple iterations where you try to solve it so that you go from one value where you're given, and you try to get to the minima, which is normally occurs such as the parabola at the bottom of the parabola if it's an upside down one, or if it otherwise you might have two minimas if it's the other way around for a parabola. So to solve it, you will need to take the derivative of the function that you are given, such as right here, dx is equal to dy dx is equal to d of x plus 7 squared plus 2x over dx, and that will be equal to 2x plus 7 squared x plus 7 plus 2. So in order to solve it, this is the general equation you will use to solve it. So right here there's an x1, which is the next value we're trying to find, equal to x, the initial value minus the learning rate times the derivative. So here I wrote it, and so that you are able to see how the steps goes from one iteration to another. And as you go, you start to, I just chose a random values of 7 so as my initial condition, and then I work to 15.5 for this x1. Then you continue to do this for iteration 2 just to show another example, and that will work as do the same equation as before, but instead of using the initial condition, you use the x1 instead of x0, so you get 15.5, which is seen here, and you will do the same. Everything else will be the same, except every x will be substituted in for x1 instead of the initial x. And then as you solve down, you will get 14.15 in this for x2, and then you will continue to do this until you reach the minima, which is for this function in particular, which is negative x comma 15, such as the value of that would be 15. So to think about gradient descent, you can also think of it as a graph, such as trying to find the best possible fit for this graph. So this is more directly correlated to machine learning, so that you normally go through multiple iterations and it will try to get the best possible fit for the data that you are given, such as if you use the prices of houses over time, as I did over the, so that would, and then you plot them all on a graph, and then you try to find the best fit line using gradient descent. At first you'll start to be a very not so close to what you really expect the general trend to be for the gradient descent, but then as you continue to go, it gets closer and closer towards what you actually want it to be, and in the end it will lead to be the best fit graph. Then you will need a learning rate in order for this to occur. So this won't really happen in 3 steps. Normally it will happen in multiple different steps, and that's why you usually use a computer for gradient descent, and that's the main aspects of machine learning and gradient descent combined. So this is a very common way of using it, and it's trying to optimize the learning of an algorithm to get to a local or global minima, normally using the negative derivative, or in other words gradient, which is why it's called gradient descent. And this is normally seen as going down a mountain if you were to visualize it, and that would be more towards trying to find the global minima in most cases, because it could commonly get caught in local minima, but if you are able to, you'll be able to find the global minima. And thank you for your time. That is gradient descent.